Ah, yes. Okay. So the next example I want to talk about is also an inequality example, except that this particular inequality example also involves an absolute value. Solving equations and inequalities with absolute values in them, in my experience with this course, has been something that causes quite a bit of difficulty for students. And fortunately, the resolution to those difficulties is pretty straightforward. So I'm hoping to give you a flavor of how that works. Here we want to solve the absolute value inequality that says the absolute value of u minus 2 is greater than 3. The question is also asking us to graph the solution on the number line. You notice that this is objective number 61. It's actually the very last objective in unit number 1. So if you make it to this objective before the objective is all due, then you're in really good shape. So let's talk about how to solve this particular inequality by looking at a strategy. And the strategy for solving any inequality which is more complicated than the one that we just did a minute ago, the strategy that I like, anytime you're not sure how to proceed, is to forget for the moment that it's an inequality at all. Make it an equality. In other words, put an equal sign there. And our strategy is going to be to use that equality to cut up and test intervals on the number line to see which ones of them are part of the solution and which ones are not. So here's what that's going to look like. First, we're going to solve the equality, the equation, absolute value of u minus 2 is equal to 3. How are we going to do that? Well, here's the trick that people forget about absolute values. We can make an absolute value in an equation go away, as long as when it goes away, it leaves behind two different things, a plus and a minus, a positive solution and a negative solution. So when an absolute value goes away, it leaves a plus or minus on the other side and gives us really two equations to solve. After we've solved that equation, that's going to define several intervals along the number line. It's going to cut our number line into pieces. It's then going to be our job to test each of those pieces, test each interval that this equality defines on the number line. And by testing, what I mean is we're going to look at the original inequality and see if those intervals solve the original inequality. And then just like in our previous example, we'll visualize our solution on the number line and we'll write out some interval notation for the solution at the end of the day. So first things first, let's forget that this is an inequality for a minute and replace that greater than sign with an equal to sign. So now I need to unwrap the u. I need to get the u by itself. And the outermost thing that's happening on this equation to the u is that absolute value. So let's get rid of that absolute value. And the way to do that is to split it into two pieces. One piece where we take a positive solution, the other piece where we take a negative solution. In this example, what that looks like is we're going to have u minus 2 on the left-hand side. But on the right-hand side, one of our equations is going to have a positive 3. The other is going to have a negative 3. So now I have two equations to solve. 2 is more than 1, so this is a little bit more complicated than it was, but our absolute value is gone, and so that should be good news. And solving each of these pieces just requires a single step, namely adding 2 to both sides. After having done that, we get two values of u, which solve the equality in this example. U equals 5 and u equals negative 1. So that was the first step. Forgetting for the moment that we started with an inequality, we solved the equation and got these two solutions. I'm going to sketch those right here on the number line and put a little equal sign on top of each of them to remind myself that it's at those 2 points that the absolute value of u minus 2 is actually equal to 3. Just a quick note about what this means. So one way to interpret an absolute value. One way to interpret what an absolute value means is to see it as a distance. So if I have the absolute value of something minus something else is equal to 3, what that really means is it's saying that the distance on the number line between two quantities is equal to 3. What are those two quantities in this example? They're u and 2. So one way to interpret the equation that we just solved is we were looking for those numbers that have the property that the distance between that number and 2 is equal to 3. So what numbers are 3 units away from 2 on the number line? And you'll notice that if 2 is right here on the number line, then if I go 3 units to the right, I'm going to find one of my solutions, 5. And if I go 3 units to the left, I'm going to find my other solution, negative 1. So this helps us to kind of understand what an absolute value is doing in the context of this equation. Okay, so we know where equals is the case. What that does for us is it cuts up the number line into 3 pieces, 3 intervals. And our job now is going to be to test each one of those 3 intervals to see if numbers which lie in that interval solve this inequality or not. So I'm going to label my intervals from left to right. I'll call them A, B, and C. So A is the interval from -infinity up to -1, B is the interval from -1 to 5, and C is the interval from 5 up to +infinity. And the name of the game is going to be to go into each one of those intervals and pick a number, any number at all. So as convenient as you want it to be, as long as it's in the interval that you're testing, and plug it back into the original inequality that we were trying to solve. If it satisfies the original inequality, if it makes a true statement, then we're going to include that entire interval as part of our solution. If it doesn't, then we're going to exclude that entire interval from our solution. So I'm just going to make a quick little chart here of the 3 intervals that we're going to test, the values that we choose inside of those intervals, the test itself, and then the sort of answer. Are we going to include that as part of our answer or not? So for the first interval, interval A on the left, let's choose a convenient representative of that interval, -2, for example. I can choose, again, any number that I want to that's a part of that interval, so I'm just going to choose one that's going to make my arithmetic as simple as possible. U equals -2 is probably as good as we can do here. So I'm going to plug that value, -2, into the original inequality. Absolute value of -2 minus 2, is it greater than 3? Well, using the order of operations, let's evaluate -2 minus 2, -4. Take the absolute value on the left-hand side, absolute value of -4 being 4, and then ask, is this a true statement? Is 4 greater than 3? And the answer is yes. So when we chose a number which was in interval A and plugged it into the original inequality, we got a true statement. And because of the way that we're approaching this problem, that means that not only does -2 solve this inequality, so does every other number that's a part of that interval solve this inequality. So our answer, our solution to this inequality is going to include the entire interval of numbers from -infinity up to -1. So we want to include piece A. What about piece B? Let's choose a convenient number inside of the interval from -1 to 5. Let's choose 0. 0 is always a nice one to work with if you can get away with it. If we plug 0 into this inequality, we'll get the absolute value of 0 minus 2 on the left-hand side, which is the absolute value of -2, which is 2. And is 2 greater than 3? No, it's not. So piece B we don't want to include as part of our solution. Again, if any number inside this interval does not satisfy the inequality, then no number inside that interval will satisfy the inequality. So because 0 doesn't work, neither does any other number between -1 and 5. And finally, for piece C, let's choose a number, I don't know, how about u equals 8? If I plug that number into my original inequality, I'll get on the left-hand side the absolute value of 8 minus 2, which is the absolute value of 6, which is 6. And is 6 greater than 3? Why, yes, it is. So sort of tidy up here. We tested all 3 of the intervals, which may or may not be part of the solution to this inequality. And we found out that interval A and interval C both are part of the solution, while interval B is not. So we have now kind of a visualization of the solution of this inequality on our number line. Let's see if we can make it a little bit more precise. Looking again at the original inequality, we have a symbol here, actually it should say greater than, not less than. Let me fix that. So in the original inequality, we have absolute value of u minus 2 is greater, but not equal to 3. What does that mean for us? It means that we shouldn't include the points at -1 and at 5, because those were the points at which the absolute value was equal to 3. So again, we're going to put open circles there instead of closed circles to indicate we're not including -1, we're not including 5, because at those values of u, we end up with an equal sign and not a greater than sign. All right, so how do we translate this all into interval notation? The degree of difficulty here is that we actually have 2 intervals that are part of our solution to this inequality. So we need a way of taking both of those intervals and including them both as part of our solution using this notation. Well, one piece at a time. Let's talk about piece A. Looking at the lower and the upper limits of this interval, A has no lower limit at all. It goes all the way to -infinity if you like. and its upper limit is -1. So in interval notation, we'll have -infinity comma -1. And then we just need to decide, are we including -infinity or are we including -1? Before we do that, let's talk about interval C. Interval C has no upper limit. It goes all the way to +infinity. Its lower limit, on the other hand, is 5. Now let's go through and decide whether or not each of those limits is a part of our solution or not. Do we want to include it in our interval notation or not? Well, -infinity, for starters, because it's an infinite quantity, it's not a number, we can never include it in our solution. So, round parenthesis. Infinities always get round parentheses in our class. How about -1? Well, we decided, again, because the inequality is greater than but not equal to, that we don't want to include -1 either, because that makes u minus 2 absolute value equal to 3. So we'll put a round parenthesis at -1 as well. For the same reason, we get a round parenthesis at 5, and we also get a round parenthesis at +infinity. So now we've written interval notation for each of our two pieces. The last thing we need is to glue those two pieces together to make them a single set that solves this inequality. And all we need to do is put in one more symbol, a little u. This u stands for a union. And what it means is that our solution includes both of the intervals that are listed here. And so in interval notation, the final answer for this problem is the open interval from -infinity to -1 union the open interval from 5 to infinity. So this was an inequality problem that also had a lot going on.